It's a tremendous honor to be here included in this great meeting, and I want to thank Irfan for the kind invitation to participate. So I see I'm not alone in including the topic of noise in my talk, and that makes sense. It's kind of a running theme in the Clark group. And as I remember John saying on more than one occasion, one person's noise is another person's signal. So, but the kind of noise I'll be talking about actually has nothing to do with qubits or even superconductivity. But what I want to do is talk about how some of the projects I've worked on had their roots in my time in the Clark group. So it'll be a little bit of a personal look back. And to start, I'd like to just say I'm very happy that there are a few of us here, at least from IBM. I think that's very appropriate because John has had such a tremendous impact on the IBM Research Division. Here's a partial genealogy we came up with. So there are 10 people, students and postdocs, that have come from John's group to the IBM lab, and this just includes the first generation. I can tell you that the name John Clark is highly respected in the hallways of the IBM labs. When it comes to quantum information, people at IBM are very well aware of who are the leaders in the field and how many of them have connections to John. And of course, many of them are in this room. So sometimes I like to tell my management, hey, I know those guys. I went to school with some of them. And in case they don't believe me, I can show them this paper. It's already been referred to quite often. This really groundbreaking paper by John Martinez, Michel Deveray, and John Clark. By the way, we had 5 Johns in the group at that time. And I can point to the acknowledgments where I was generously included amongst a list of much more distinguished contributors. I can pretty much guarantee this is going to be the only time my name is in the same paragraph as Tony Leggett's. But it was a great time. I have very fond memories of that time. My contribution was working on the gas handling system. I got to work closely with Michel, and that was a real pleasure and learning experience. You saw a little bit of that in Fred's picture. That was the wooden panel there. I can assure you that anything inelegant on that was not due to Michel. He's a very careful experimentalist. But I do remember it as a time of great camaraderie and teamwork and everybody pulling together to really make something important happen. I even remember an afternoon where John came with a giant soldering gun and spent time trying to pin down leaks on the dilution fridge unit. So I thought that was great. So looking back, I really do feel like I got to be a witness to history in the making. Now, there were a couple of events that happened during my time in the group that maybe had more direct relevance to what I ended up working on. The first involved my roommate, of all people. So I shared an apartment with a fellow physics graduate student named Tycho Slater. And I could tell you lots of stories about Tycho, but that would take the whole talk. But he was a student of Professor Hans, and he worked on this experiment, which you've already heard about from Kristen's talk, to measure nuclear spin noise, teaming with Claude Hilbert and John Clark. So this effect was first pointed out by Felix Bloch in his original paper, the one that had the Bloch equations. And Bloch pointed out that even in the absence of an orienting magnetic field, if you have a collection of n nuclear spins, there's going to be a net polarization of order square root of n due to incomplete statistical cancellation. So it's kind of like flipping a box of coins. Roughly half are going to be up, half are going to be down, but you'll get some excess of order square root of n. So they measured that. They were the first ones to measure it. They used a squid and an inductive pickup loop, and it showed up as this excess spin noise, that little bump there, and there it is with the background subtracted. So I remember Tycho coming home very excited when they had seen this effect. And I have to admit, I thought it was interesting, but I didn't quite understand what the big deal was. Actually, it was only a little bump. And I certainly didn't anticipate I would spend a large part of my career making use of this effect in one way or another. But it's one example of how noise can be useful. And by the way, I contacted Tycho in preparation for this talk, and he remarked that he still considers this one of the more interesting things he's done in his career. So the other event had a more immediate impact on me. So as Dale mentioned in his talk, I'd been working with him on an experiment to measure thermoelectric effects in superconductors. He He referred to this as a fun time, and it was certainly fun working with him, but the experiment was a bit frustrating at times. It took me a couple years to get some data. So this would have been the 1982-83 time frame. So getting data was fun, and I could at least begin to imagine that maybe there was light at the end of the tunnel, and I'd graduate one of these days. And then this happened. John came back from a meeting very excited. He had heard about this new instrument, the scanning tunneling microscope, and we had a conversation. I don't remember the details, but he was such a great motivator. We had agreed at the end that I would finish up my current round of experiments, and then help build a UHV STM for the group. So I knew then that I probably would not be graduating anytime soon, which was true, but it was totally worth it. I learned so much, and it's what got me hired into IBM, and again, I got to work with some great people. By the way, this is hard to imagine, but at this time, there were probably less than a dozen working STMs in the world. So this was the STM team. I got to work with David Abraham, Eric Gantz, and Ruth Ellen Thompson. And I tried to find a group shot. This was the best I could find. This was from one of the great dinner parties that John and Greta would throw. Always great, gave a lot of great group spirit. I think it must have been my going away party, because they gave me a barbecue. And you can see Fred there, and Eric, and Ruth Ellen. So I just want to say I feel very proud to have been part of the group, and I thank John and wish him all the best going forward. Okay, so let me now talk about magnetic resonance, which I call spin noise meets scanning probes. So kind of the marriage of those two themes. Our motivation for this work is we'd like to be able to do MRI of molecules. That's the dream anyway. So I'm going to talk about two very different approaches, one based on ultrasensitive force detection, which we call magnetic resonance force microscopy, and the other based on these quantum sensors, nitrogen-vacancy centers in diamond. And again, I've gotten to work with great people. I'll try to acknowledge them as I go. I especially want to mention my longtime collaborator and manager of the group, Dan Rugar. So this is the dream. We'd like to be able to take 3D images of molecules to do for molecular structures like proteins, what the STM did for surfaces. Take an image and look with atomic resolution, but in this case, look below the surface, atom by atom, in 3 dimensions. And ideally, you'd be able to work with individual molecules in situ and even be able to learn something about what kind of atom you're looking at. We're a long way from being able to do that, but if you could do that, it would be quite significant. So magnetic resonance imaging, or MRI, is one technique that is truly non-destructive. It gets around the problem of radiation damage, and it is 3D. It works by detecting the nuclear magnetism of the nuclei in your body, primarily the hydrogen, and in a magnetic field, they'll process at a characteristic frequency that you can pick up with an inductive coil. The problem is that nuclear magnetism is a very weak effect, and it takes about at least 10 to the 12 nuclear spins to get a pixel's worth of information. So we have many orders of magnitude of improvement that would need to be done. So there's a very creative guy up at University of Washington named John Seidels who pointed out that maybe you could do much better with a force detection. So this is a very simple concept, at least, that if you have 2 magnets, one magnet being the spin or spins you're trying to measure, and one being a ferromagnet, they'll either attract or repel, depending on if they're aligned or anti-aligned. And if one of them is on a flexible cantilever, it will deflect, and you can measure that force. And in this geometry, the force is given by the product of the moment times the gradient, the lateral gradient. Just to set the scale, the force from a single proton in a gradient of 10 to the 1 million Tesla per meter is about 10 to the minus 20 newtons. So that's actually too small for us to measure. We're not able to measure a single nuclear spin, but we can measure of the order of 100 of them, net spins. We were able to measure a single electron spin in a slightly lower gradient that gave a force of about an attonewton. And all of these forces are much, much smaller than any electrostatic or van der Waals forces at that scale. So we need a way to distinguish them. To do that, we use magnetic resonance. If you apply a RF field at the precession frequency, you can change the precession angle and even cause the spins to invert. And if you do that at the cantilever frequency, you'll build up an oscillation. Also, because the field from the tip is very inhomogeneous, only those spins within a thin resonant slice will be affected, and that gives you your lateral resolution. For this, we use very sensitive single crystal silicon cantilevers. These are very thin, very high Q at low temperature. They were made by Ben Chewy, who actually was a student of Tom Kenny, who was a student of Paul Richards. So there's a Berkeley connection there. And the reason we operate at low temperature is because the dominant noise source is thermomechanical noise, just like the analog to Johnson noise in a resistor. So we operate in a dilution fridge, and we can get down to about, in this case, 0.7 attonewtons per root hertz, which for many years was a world record for mechanical force detection. I think it's since been surpassed. So now we come to statistical polarization, which I had introduced before. And if you want to measure small volumes, then you have to be able to deal with this statistical polarization. If you look at mean polarization, it's just some fraction of the total number of spins. So that goes as n. But statistical goes as square root of n, and at some point they're going to cross. And for reasonable conditions, that occurs at about 1 million spins, which for typical organic materials corresponds to a volume of about 30 nanometers cubed. So if we want to measure smaller volumes than that, we have to measure statistical polarization. So the idea there is that we're measuring a noise power. So this is a simulation of 1,000 spins, and we are causing the ensemble to flip every so often, synchronously. But then, in addition, there's a certain random spin flip probability per unit time. And if you just run the simulation, you find that you get a spatially varying or time varying amplitude and sign, and the RMS amplitude goes as square root of n, the variance goes as n. So you just stick this into a spectrum analyzer or a lock-in amplifier and measure your signal, and that's what you measure. One nice thing is you don't need to wait a repolarization time to do this because you're always measuring. And that's good because the T1s at these low temperatures can be very long, can be hours or more. So this is now data. It's taking a signal like I showed and putting it in a spectrum analyzer. And it's really the mechanical analog of the squid measurement that I showed you earlier. So it's the, oh, that's weird. That's supposed to line up. It's the cantilever thermal noise is this broad background, but then you clearly see this peak sticking out due to the spin noise. And that's proportional to the number of spins. Now we can actually do a little bit better by using a lock-in amplifier because there's a definite phase to the flipping. So here you see the in-phase and quadrature signal. This is from some nuclear spins. So the noise level here is just the cantilever thermal noise, and you clearly see a greater noise, and that's the spin noise. So we take the difference in the variances, and that's our signal. And then we can take that and use that as our imaging signal. Just quickly mention as an aside, when we're able to see the fluctuations in real time, we can play some clever games with them that are kind of fun. You can actually rectify the fluctuations. You just put in an extra flip whenever you see the spin signal going negative. So this is the fluctuation, and then we put in these extra flips, and you see that we're getting a rectification. So it's kind of like a little Maxwell's demon. We're creating order or mean polarization where there originally was none. And this was done by our postdoc Rafi Budakian. But let's go ahead to imaging. Oh, really? It says, oh, you're right. So I got to move along. So this is an example of imaging a biological system, tobacco mosaic virus. We put it on the end of the cantilever, apply our protocol, and scan it over the tip. and we could get images that look like this. So this is like an MRI image. It's different slices, and each slice shows basically the amount of proton signal. So you can see these rod-like structures. It agrees very well with an SEM taken after the fact. But of course, this is a 3D data set, so we can take a slice perpendicular to the sample, and we see the virus in cross-section on top of a 1 to 2 nanometer thick layer of proton material, which is basically adsorbates, hydrogen or hydrocarbon. So that's about where we get with the force detection. It corresponds to about a factor of 100 million improvement in volume resolution compared to the best conventional MRI. So the remaining minutes, I'll just talk about this completely different approach, but with the same goal in mind, using nitrogen vacancy centers as atomic scale magnetometers. So we already heard an introduction to these in David Ausschlam's talk. And they're kind of defect or color center and diamond. You shine green light in, you get red light out, and the amount of red light tells you what the spin state is. So each of these, there's a scanning fluorescence image. Each of these bright dots is a single NV center. So you can apply microwaves, and you see the count rate go down as you excite various transitions of this ground triplet state. And the splitting immediately tells you what the magnetic field is. So it's a magnetic field to photon transducer. Now we can do all the standard magnetic resonance tricks with this technique. In particular, we can get enhanced sensitivity to AC fields by using Hahn echo. So we do the Hahn echo, which normally would refocus the signal, but if you put an AC field on, you get a difference in precession rates in the two halves of the echo. And you get this cosine response, which is the count rate as a function of the strength of the applied AC field. So I think of this in terms of squid response, only it's a different, you're transducing field to count rate, and the period, instead of being set by phi naught, is set by the length of the echo, or 1 over it. So the longer the echo, the more sensitive you are, and you end up with this expression, because ultimately you end up with T2 constraints. And for T2 in isotopically pure materials, you can get over a millisecond, which gives you a field sensitivity of about 4 nanotesla in 1 second of averaging. Now by squid standards, that doesn't sound very impressive, but it's this combination of nanotesla sensitivity with a nanometer scale sensor that makes this unique and potentially interesting. And that's kind of in the ballpark you need to be for single proton. So one of the first things we did was to measure see if we could measure spin noise from nuclear spins outside the diamond. So we teamed up with David Ausschlam's group that was growing these very nice isotopically pure carbon-12 layers that gets rid of one source of decoherence. We spun on a layer of PMMA, just something containing lots of nuclear spins, and then we had NVs that were grown about 20 nanometers deep. And this shows the T2, or the spin echo decay. The T2 is very long in these materials, over half a millisecond, even at room temperature, which is nice. We did a double resonance technique. We applied RF fields to flip the nuclear spin synchronously with the spin echo and disrupt the spin echo. And we got a clear signature, a depression in the spin echo response. It varies with field, as you would expect. If you look at the field as a function of, look at the frequency as a function of field, you get 42.6 megahertz per Tesla, which is the gyromagnetic ratio of hydrogen. So we were able to see the spin noise from the hydrogen. And then the final, or the next step, then was to do a simple imaging experiment. So, of course, it's simple in practice. It's never as simple, simple in theory. There are always gotchas. But basically, it was just to scan a particle of PMMA, like the PMMA film, over the NV and verify that we could get some imaging. So in this case, the NV center was even shallower, about 10 nanometers deep. We could get images that looked like this. This is a 2D image, and it's not a topographic image. It's an image of the fluctuating field strength from the nuclear spins, so the spin noise. And if you look at the resolution, it turns out it's about 12 nanometers lateral resolution, which is comparable to the depth of the NV, which is about what you would expect. So the final slide here is just showing that we can detect individual nuclear spins if they're close enough to the NV center. So this is a signal from some C13s that are in the diamond lattice. And it's a form of noise correlation spectroscopy. I won't go into the details, but basically it's kind of like a giant Ramsey fringe. You put on pi pulses at the carbon-13 precession frequency. You don't know the phase, but it has a correlation in time, so you measure it again, and you'll get a varying correlation with the time between them. And that gives you, the Fourier transform gives you individual peaks which represent different carbon-13s at different locations in the lattice. So I'll end here with my acknowledgments. And again, I want to thank the IBM team, Dan, Mark Sherwood, and Charlie Retner. We've had a string of great postdocs, collaboration with David Aushalom and his group, and funding from IBM, DARPA, ARO, and the NSF. And thanks again, John, and thank you for your attention.
Thank you for an interesting talk. We have a few minutes for questions. It's hard to see you guys with those limelights. There's a question.
I guess two-part question. Firstly, well, thanks for the great talk, really interesting. What do you think is the prospect for how far NVs will be pushed, I guess even ultimately? And also, do you see any other candidate sensors that you hope to explore after doing the force microscopy and the NV centers?
Yeah, in terms of the NVs, I think that you always learn sort of the dirty little secrets when you work with them. And so they do have their challenges. It's the decoherence of the near surface. You know, the coherence times can be very long when they're in the bulk, but then as they get close to the surface, it's much harder to keep that long coherence time. So there is progress on that, and I think that will be one of the keys to making this work. We're certainly interested in these alternative spin centers, like we heard about yesterday. It's hard to make predictions. You know, we've been at this a long time, and we've pushed it a fair ways, but you know, getting that last bit is challenging.